The Large Hadron Collider, or LHC for short, might sound like something out of science fiction, and honestly, it kind of is. This machine is essentially a giant racetrack, but instead of cars, it smashes subatomic particles together at nearly the speed of light. Pretty mind-blowing. Think of it this way. The LHC is like a time machine, allowing us to see what the universe might have been like just after the Big Bang. It's a marvel of engineering, a massive ring stretching 17 miles wide and buried a whopping 175 meters underground. And it's not just in one country, but built in collaboration between France and Switzerland, displaying international teamwork in the pursuit of scientific discovery. This scientific powerhouse comes with a hefty price tag, though. The LHC cost a cool $4.5 billion to build and even more to maintain and upgrade. But the payoff has been significant, helping us unlock secrets of the universe at its most fundamental level. So, how does this wonder machine work? It's all about velocity. The LHC whips subatomic particles around its track until they are practically flying at the speed of light, making thousands of laps per second. How do they achieve such incredible speeds? With the help of incredibly powerful electromagnets generating a magnetic field thousands of times stronger than Earth's own. Now, some folks were understandably worried about the impact of such a strong field on nearby electronics, and even the planet's magnetic balance. But that's just the setup. Once these particles reach their top speed, nearly 1,000,000 times faster than sound, they smash into each other head-on. That's what the LHC is designed to do, and it's this collision that scientists are truly interested in. It's through these collisions that we hope to learn more about the fundamental building blocks of our universe. The crash between these particles is no joke. It unleashes a huge burst of energy, spawning a whole bunch of different subatomic particles. These new particles scatter in all directions, but they're like fireworks. Here 1 minute, gone the next. Most of them disappear almost instantly. Fascinatingly, by changing up the types of particles they smash together, scientists can potentially discover entirely new particles hiding within the mayhem of the collision. To capture these fleeting moments, they've built incredibly sensitive detectors around the collision points. Think of these detectors as superpowered cameras recording every detail of the crash. The only problem? All this action creates a massive amount of data, over 15 petabytes every year. That's like having a whole library of information dumped on you every single year. Sifting through all this data takes some serious time and effort, but within this treasure trove lies the key to unlocking some of the universe's biggest mysteries. The LHC has already achieved something remarkable. It's challenged our current understanding of the universe, shaking things up in the world of physics. Ever wondered how the universe works? Scientists have this amazing blueprint called the Standard Model, kind of like an instruction manual for everything in the universe. It explains how all the tiny building blocks like quarks and electrons interact with each other, almost like following directions to build a Lego set. The Standard Model is pretty impressive, describing everything from the tiniest particles to the forces that hold them all together. There are these things called quarks, for instance, and they come in 6 different flavors, each with its own unique properties like electric charge and mass. Then there are leptons, like electrons, which are essential for building atoms. And don't forget the bosons, the busy bees that carry forces like electromagnetism and act as the glue holding quarks together. But here's the catch. The Standard Model, for all its brilliance, isn't entirely complete. It leaves some big questions unanswered. That's where the LHC comes in. By recreating powerful collisions like the Big Bang, it's uncovering mysteries that our current understanding can't explain. Take a particle called the beauty quark, for example. The LHC's findings are challenging our entire picture of the universe in unexpected ways. Scientists made a surprising discovery. When beauty quarks break down, they don't quite follow the rules laid out by the Standard Model. According to predictions, these quarks should change into muons and electrons at similar rates, But experiments at the LHC showed something different. This unexpected twist suggests there might be entirely new particles or forces at play, which goes against our current understanding. And that's not all. The LHC's collisions are also producing bizarre particles that the standard model can't account for. One such example is the pentaquark, a whole new kind of particle made up of 5 quarks, instead of the usual 3 found in protons and neutrons. This discovery of the pentaquark is a significant development, opening doors to a whole new world of possibilities. It suggests the existence of previously unknown quark combinations just waiting to be unearthed. But the truly exciting aspect lies in its implications for our comprehension of the universe. The pentaquark hints at the presence of mysterious subatomic forces that we're only beginning to grasp. The discovery of the pentaquark was a groundbreaking moment. The statistical deviation observed was a remarkable 15 sigma, showing the LHC's incredible precision and power. In the world of particle physics, achieving a deviation of 5 sigma is considered the gold standard for confirming a particle's existence, so a deviation of 15 is truly exceptional. And the surprises didn't stop there. The LHC also discovered another exotic particle, the tetraquark, further challenging the standard model. This 4-quark wonder, named TCC+, is one of the latest additions to the world of particles. Think of it as a quartet of quarks with 2 heavier charm quarks and 2 lighter ones, all bound together by the strong nuclear force. Similar to the pentaquark, its discovery suggests the existence of even more quark combinations waiting to be explored. Interestingly, the TCC+ holds the potential to unlock the secrets of quantum chromodynamics, or QCD for short. These are the fundamental rules governing how quarks interact under extreme conditions, and they form a crucial piece of the standard model. It's a complex puzzle, but broadening our understanding of QCD could lead to groundbreaking discoveries about the very nature of matter itself. The LHC detector played a pivotal role in uncovering the tetraquark. Scientists were able to catch a fleeting glimpse of the TCC+'s signature amidst the chaos of proton collisions. However, the TCC+ is a short-lived entity, much like a fleeting spark before it transforms into other particles. In a surprising turn of events, the LHC revealed that the Higgs boson, a critical piece in our understanding of the universe, is heavier than initially predicted. But what exactly is this elusive particle? The Higgs boson, often formally called the Higgs particle, is a fundamental building block within the standard model of particle physics. It arises when the Higgs field, another cornerstone of particle physics theory, becomes agitated through a process known as quantum excitation. Within this model, the Higgs boson reigns supreme in terms of mass. It's a scalar boson, meaning it has no spin and a positive intrinsic parity, but lacks electric or color charge. However, its existence is fleeting. It rapidly decays into other particles almost immediately after formation. Now let's look deeper into the concept of the Higgs field. Imagine an invisible field spreading out over the entire universe. This field possesses a unique characteristic. It always holds a non-zero value, even in the vast emptiness of space. This property, through a mechanism known as the Higgs mechanism, is responsible for imbuing various particles with mass. Think of it metaphorically. The Higgs field throws a universal party, inviting all the particles to join. The interaction during this party gives mass to the particles while breaking a fundamental symmetry of the universe. We owe this profound insight to physicist Peter Higgs and his colleagues, who proposed the ingenious Higgs mechanism in 1964. This groundbreaking theory not only explained how particles acquire mass, but also predicted the existence of the Higgs boson itself. It's like solving a complex puzzle. If their theory holds true, a particle with specific characteristics must exist, and voila, the discovery of the Higgs boson beautifully corroborated their predictions. The Higgs boson, often nicknamed the God particle, finally emerged from a 40-year scientific quest in 2012. Scientists at CERN, using the powerful ATLAS and CMS detectors within the LHC accelerator in Switzerland, unearthed this long-sought-after particle, perfectly matching the predicted properties of the Higgs boson. The discovery of the Higgs boson was like finding that crucial missing piece. The significance of this breakthrough was undeniable, leading to the Nobel Prize in Physics being awarded in 2013 to Peter Higgs and François Englert, two key figures behind the Higgs mechanism theory. However, it's important to acknowledge the collaborative nature of this achievement. Several researchers, independent of each other, contributed crucial pieces to the puzzle between 1960 and 1972, laying the groundwork for what would become known as the Higgs mechanism. Fast forward to recent times, with the LHC accumulating more data, scientists made a surprising discovery about the Higgs boson. Its mass was found to be greater than 125 giga-electron volts per square speed of light. This revelation sent shockwaves through the scientific community. A heavier-than-predicted Higgs boson could necessitate a re-evaluation of our fundamental understanding of the universe. Does this mean we need to scrap the standard model entirely? Not necessarily, but it certainly hints at the possibility of new particles or forces existing beyond our current knowledge. It's like discovering a completely new puzzle piece, one that could potentially revolutionize our perspective on the universe. Furthermore, the heavier Higgs boson has spurred renewed exploration of the Higgs field and its role in shaping the universe. The mysteries surrounding the Higgs boson continue to fascinate scientists. Research into this elusive particle is poised to intensify during the LHC's third cycle, particularly after the planned high-luminosity upgrade in 2029. This upgrade will significantly increase the number of collisions within the accelerator, offering researchers more opportunities to uncover anomalies that deviate from the standard model. CERN estimates a staggering 15 million Higgs boson particles being produced annually after the upgrade, a substantial leap from the 3 million generated in 2017. This abundance could prove instrumental in identifying different flavors of the Higgs boson. Theories beyond the standard model predict the existence of up to 5 distinct forms, some potentially less frequent than the fundamental Higgs. Even before these advancements, compelling evidence for a magnetic Higgs boson has already been found. But what exactly makes the Higgs boson so important? The Higgs field plays a central role in shaping the universe, especially in its infancy. It dictates the properties of the vacuum in our spacetime, influencing the existence of matter interactions and, crucially, the mass of all fundamental particles. Without the Higgs field, and by extension the Higgs boson, the cosmos would be devoid of atoms, stars, and even life itself. So why the nickname God particle? This moniker gained traction after the Higgs boson discovery. It's believed to have originated from Nobel laureate Leon Lederman, who initially intended to call it the goddamn particle due to its elusive nature. However, publishers changed the title to The God Particle for his 1990s book on the Higgs boson. The connection between the Higgs boson and religion has been a point of debate among modern physicists. However, the significance of the Higgs boson and the Higgs field cannot be understated. They are fundamental to the very existence of mass in the universe. Without them, there would be no stars, planets, or even living beings, a fact that partly explains the dramatic nickname. Beyond mere characterization, scientists are fascinated by the Higgs boson for two key reasons. First, they seek to understand the origin of the physical vacuum, the space we inhabit in the early universe. Second, they aim to comprehend the stability of this physical vacuum. The Higgs field is unique in that it imbues the physical vacuum with a non-zero expected potential energy, a factor that profoundly impacts our universe. Scientists believe this energy potential is responsible for the existence of both the electromagnetic force, which has an infinite range, and the weak force, with its very limited range. To gain a deeper understanding, scientists need to delve into how Higgs bosons interact with each other. This requires creating collisions that produce pairs of these elusive particles. While the discovery of the Higgs boson has illuminated how other fundamental particles acquire mass, the origin of the Higgs boson's own mass remains a mystery. The current theory lacks a specific symmetry that would guarantee this mass and prevent unforeseen instabilities. There's a theoretical possibility that quantum fluctuations could disrupt the very fabric of the physical vacuum itself. However, these disruptions, if they occur at all, would unfold on timescales vastly exceeding the known age of the universe. Nevertheless, scientists are actively searching for additional particles that share similarities with the Higgs boson. The existence of such particles could hint at new physical principles beyond our current understanding, principles that might be necessary to explain the stability of the Higgs boson's mass. These considerations underscore the critical need for further research, more data collection, and potentially access to particle colliders with even higher energies. This ongoing endeavor, driven by hundreds of dedicated experts from around the globe, shows the commitment to solving the mysteries of particle physics. The LHC has played a crucial role in furthering the theory of extra dimensions, offering a glimpse into realms beyond our familiar three-dimensional universe. But what exactly are these extra dimensions, and why are they so captivating to scientists? Our vast universe is just a sliver of a much grander reality. This is the idea behind the theory of extra dimensions. It proposes that beyond the length, width, and height we experience, there could be additional dimensions, hidden layers, waiting to be discovered. These dimensions might be tightly curled or incredibly small, far too minuscule for our current technology to detect. Think of it like viewing a thread from afar. It appears one-dimensional, but upon closer inspection, you see its depth and width. Similarly, these extra dimensions could be all around us, existing unnoticed due to their diminutive scale. But why are scientists so interested in dimensions beyond our familiar three? They're on a quest to unify the fundamental forces of nature. Remember how the Standard Model successfully describes 3 of the 4 fundamental forces? Gravity, however, remains the outlier. It's significantly weaker than the other forces like electromagnetism and the nuclear forces, and integrating it into the Standard Model has been a long-standing challenge. Here's where the concept of extra dimensions becomes particularly intriguing. According to the theory of extra dimensions, gravity might be the key to understanding its own weakness. The theory proposes that gravity, unlike the other fundamental forces, bleeds off into these hidden dimensions, explaining why it appears so feeble compared to its counterparts. The Large Hadron Collider, LHC, plays a critical role in exploring this idea. By delving into the subatomic realm, the LHC's history of uncovering surprises, from unexpected particle collisions to the peculiar behavior of quarks, hints at phenomena beyond the Standard Model's grasp. These anomalies might be the whispering signatures of extra dimensions. One key aspect lies in the LHC's ability to accelerate particles to incredibly high energies. When particles collide at such velocities, they shatter into their fundamental constituents, revealing the underlying forces and their interactions. Scientists meticulously analyze these collision patterns and decay sequences, searching for any clues that might hint at the existence of extra dimensions. Think of a successful high-energy collision unleashing a torrent of subatomic particles. Using only the known particles involved, scientists can calculate the total energy and momentum before the collision. If extra dimensions exist, however, some of this energy and momentum could be leaking into these hidden realms. Detecting any discrepancy in the expected versus the observed energy and momentum becomes crucial. Even the slightest deviation could signal the presence of extra dimensions. However, this is an immensely delicate task, like trying to hear whispers in a noisy room. The detectors require exceptional sensitivity to pick up these faint signals. Another method employed to uncover extra dimensions involves studying particle decay patterns. Specific particles decay into other particles in a predictable manner, most of which follow the standard model. However, if unknown extra dimensions are influencing these decays, deviations from these established patterns might occur. Scientists meticulously analyze these decay processes, searching for any anomalies that could point toward the influence of extra dimensions. The search for extra dimensions extends to the intriguing concept of micro-black holes. These theoretical black holes, significantly smaller than their stellar counterparts, could be produced during high-energy particle collisions within the LHC. Some researchers are making a connection between extra dimensions and the formation of micro-black holes. The hypothesis hinges on the idea that gravity, while weak in our familiar 3 dimensions, might exhibit greater strength in these additional dimensions. Consequently, the detection of micro-black holes during particle collisions could be interpreted as evidence for the existence of extra dimensions. This line of inquiry goes deeper into the interplay between gravity and extra dimensions, offering a potential avenue for their exploration. Quantum entanglement stands as one of physics' most captivating enigmas, blurring the lines between science fiction and reality. Think of 2 particles linked in such a way that the fate of one instantly determines the fate of the other, regardless of the vastness of the separation between them. This phenomenon, famously dubbed spooky action at a distance by Albert Einstein, is far from our classical understanding of how the universe operates. The mind-bending aspect of entanglement lies in its apparent defiance of well-established laws, particularly Einstein's theory of relativity, which dictates that nothing can surpass the speed of light. When particles become entangled, it seems as though they exchange information instantaneously, hinting at a form of communication that transcends the confines of space and time. However, despite its seemingly paradoxical nature, quantum entanglement doesn't violate the fundamental principles of relativity. Instead, it offers a fascinating glimpse into the bizarre realm of quantum mechanics, where particles can exist in multiple states simultaneously and exhibit behaviors that defy our everyday understanding of reality. CERN stands at the forefront of solving the mysteries of quantum entanglement, a phenomenon that pushes the boundaries between science fiction and reality. Their mission is to unlock new insights into the universe's workings by probing the intersection of quantum mechanics and general relativity. Scientists at CERN meticulously conduct experiments involving entangled particles, meticulously observing how these particles interact across varying distances. The LHC's unparalleled precision allows researchers to measure the properties of entangled particles with unprecedented accuracy. Understanding quantum entanglement could revolutionize our cosmic comprehension. If particles can be intricately linked over vast distances, could this entanglement extend through time as well? Answering these questions could fundamentally alter our understanding of time's flow. Furthermore, exploring entanglement might lead to discoveries of new dimensions. Certain properties of entangled particles hint at the existence of dimensions beyond our current perception. If entanglement indeed occurs across these dimensions, it could illuminate the structure of these hidden realms and how we might interact with them. Quantum entanglement isn't merely a theoretical concept. It's poised to be a game changer for technology. Just think of quantum computers, where entangled particles perform calculations beyond the reach of traditional computers. This opens doors for advancements in cryptography, drug discovery, and other fields demanding immense computational power. Secure communication channels, virtually unhackable, represent just a glimpse of the mind-blowing possibilities. CERN's pursuit of entanglement extends beyond the realm of black holes. They delve deeper, seeking to crack the secrets of wormholes, hypothetical shortcuts through space and time. By unraveling the mysteries of quantum entanglement, CERN pushes the boundaries of human knowledge, paving the way for groundbreaking discoveries in physics and technology. Imagine traveling through a wormhole, a hypothetical shortcut through space-time, essentially hitching a ride across the universe. This wild concept, along with the possibility of parallel universes, lies at the heart of ongoing research at CERN. Now let's look into supersymmetry, or SUSY for short. Think of it as an expansion on the standard model of physics, proposing a mirror universe where every particle has a shadowy twin, a counterpart with similar properties but distinct behaviors. For instance, each boson, force-carrying particle, would have a fermion, matter-particle partner, and vice versa. This theory holds immense promise for solving the mystery of dark matter, the vast invisible substance composing a significant portion of the universe. Supersymmetric particles could be the missing pieces of this cosmic jigsaw puzzle. Their stability, mass, and weak interactions perfectly align with what we know about dark matter. The Large Hadron Collider, LHC, plays a crucial role in studying SUSY. By recreating conditions similar to the Big Bang, the LHC allows scientists to glimpse the very foundation of our universe's laws. If SUSY particles exist, they could be produced during these high-energy collisions. Furthermore, SUSY provides a framework for understanding extra dimensions. String theory, which incorporates SUSY, requires these extra dimensions to function mathematically. SUSY helps stabilize these dimensions and suggests ways we might observe their effects, perhaps through subtle variations in the strength of forces or the mass of particles, phenomena detectable by the LHC. In essence, the LHC acts as a powerful microscope, allowing us to explore the hidden corners of the universe. The European Organization for Nuclear Research, or CERN, stands at the forefront of scientific exploration. However, its groundbreaking research into subatomic particles and the universe's fundamental laws has also attracted a fair share of outlandish conspiracy theories. One particularly alarming theory suggests CERN is attempting to open a portal to hell. Conspiracy theorists believe that CERN's experiments, which involve colliding subatomic particles at incredibly high speeds, could potentially lead humanity down a path towards an infernal realm. However, CERN maintains a clear and scientific mission: to deepen our understanding of matter and mass through the generation and study of antimatter. Antimatter, as its name suggests, possesses opposite electrical charges compared to normal matter. According to the Big Bang theory, antimatter is incredibly rare, likely formed in the very birth of the universe. Another conspiracy theory links CERN to the Mandela effect, a phenomenon where people hold seemingly widespread but inaccurate memories of past events. Some speculate that CERN's particle experiments might disrupt the fabric of reality itself, causing a large-scale Mandela effect. Finally, some theories go as far as suggesting human sacrifice occurs at CERN, fueled by a purportedly leaked video depicting ritualistic events. CERN has vehemently denied these claims, labeling them as hoaxes. It's crucial to remember that despite these outlandish theories, CERN's primary focus remains scientific exploration. Recently, CERN's Large Hadron Collider, LHC, achieved a significant breakthrough: the detection of elusive subatomic particles called neutrinos. This discovery holds immense potential for providing insights into the intense interactions between neutrinos and other particles within stars, potentially shedding light on stellar phenomena like supernovae. Neutrinos, often nicknamed ghost particles due to their near invisibility, are abundant throughout the universe, but incredibly difficult to detect because they rarely interact with matter. Ever since their discovery in 1956, neutrinos have captivated scientists with their enigmatic nature. While they are prevalent throughout the cosmos, their interactions with matter are rare. In 2021, physicists at CERN managed to detect the faint presence of 6 neutrinos. However, it took 2 years of meticulous research to confirm their existence, highlighting the immense challenges and dedication involved in this field of study. As James Boyd, a particle physicist at CERN and co-spokesperson for the FACER collaboration, emphasizes, studying these elusive particles serves as a powerful tool for unraveling the mysteries of the vast universe. The high-energy neutrinos detected at the LHC offer invaluable insights into the enigmatic realm of astrophysics. This breakthrough shows CERN's commitment to pushing the boundaries of scientific knowledge. As the research continues, the scientific community waits eagerly, anticipating CERN's next groundbreaking discovery and the profound implications it may hold for our understanding of the universe. What are your thoughts on CERN's experiments at the Large Hadron Collider? If you like this video, subscribe to our channel for more content like this. See you in the next one.